Let's prove the trigonometric ratio of 30, 60, and 45. Typically, the special angles. How are those values? How are they gotten? In this video, I'm going to show you how all those values are gotten. So let's begin by considering an equilateral triangle of side 2 units. So this is my equilateral triangle. It's going to have 2 unit sides. So this is going to be 2 units. This will be 2, and this will also be 2. Since it is an equilateral triangle, we know that one of the properties of equilateral triangle is that all the angles are equal and they are simply 60 degrees in magnitude. So it means this angle will be 60, this will also be 60, and this as well will be 60. If that the case, what I will do next is that I would like to bisect the base of the triangle. And to do that, what I will do is to draw a perpendicular line from this vertex all the way to the base of the triangle. And with this, we can clearly see that this line makes an angle of 90 degrees with the base. And therefore, we can clearly have two right angle triangles. So is that the case? If this line bisects the base of the triangle, it means the magnitude of the base from this point to this point will simply be 1 unit, as we have divided the whole base, which is 2, by 2. So this will be 1 unit. Similarly, this will also be 1 unit. So what I would like to do next is to bring out one part of the right angle triangle, and that will be this. So we said this is 2, this is 1, and let's assume this is h. Don't forget this is 60 degrees. Now the angle has been bisected as well, so it's split this into 2. This will be 30 degrees, and this is 90 as right angle. So what I would like to do now is to use the Pythagoras theorem to solve for h. So we know that according to Pythagoras theorem, the longest side, which is the value of 2, the square of it simply equals to the sum of the square of the other two sides. So that's h and 1, and that will be the square of h plus the square of 1. And we can clearly solve for h at this point. So that will be 4 equals h squared plus 1. And if I subtract 1 from both sides, we should eventually have h squared to be equals to 4 minus 1, which is indeed equals to 3. So if I take the square root of both sides, h will simply be equals to square root of 3. So now, I'm just going to get rid of h over here, and I'm going to replace that with square root of 3. Now back to our knowledge in trigonometric functions. We know that the sine of angle theta is simply equals to the ratio of the opposite side to the hypotenuse side. For the sake of those that might not be familiar with the opposite and the hypotenuse, the longest side is the hypotenuse side, while the opposite and adjacent side will vary. It depends on the side that is facing the angle. But just keep in mind, the side that is facing the angle is meant to be the opposite side. So if we are dealing with the angle 60 degrees, this side is the opposite, while this is the adjacent. However, if we are dealing with angle 90 degrees, angle 30 degrees, this side will be the opposite, and this will be the adjacent. So just keep that in mind. Perfect. So now, for now, let's focus on angle 60 degrees. It turns out that sine 60 degrees will simply be equals to the opposite, which is the square root of 3, then divided by the hypotenuse, which is simply 2. And this is how the value was gotten. Similarly, it turns out that cos 60 degrees, well, we need to write the corresponding ratio of cosine theta first. Cosine theta is simply adjacent over hypotenuse. So that's ADJ over hypotenuse. And similarly, tan theta will simply be equals to opposite over adjacent. So that's something you want to be familiar with. So right now, cos 60 will simply be equals to the adjacent, which is 1, then divided by the hypotenuse, which is simply 2. So therefore, cos 60 is nothing but half. Now what about tan 60? What would that be? Tan 60 is simply equals to opposite over adjacent. The opposite is simply square root of 3, and the adjacent is indeed equals to 1. So that will be the square root of 3, because square root of 3 over 1 is simply square root of 3. Right now, I'm no more in need of this triangle, so I would like to get rid of it so I can have enough space to write these values. For now, we have solved for sine 60, cos 60, then tan 60. So we said sine 60 is simply equals to square root of 3 over 2. Cos 60, we got that to be 1 over 2. And tan 60, we got that to be square root of 3. Good. Now, what about their corresponding value when the theta is equals to 30? Let's see how this works as well. Now, like I said, when the angle is 30 degrees, sine 30 will simply be equals to opposite over hypotenuse as usual. However, the opposite side we need to be considering in this case has to be the side that is facing the angle. So therefore, the opposite side is simply 1. So sine 30 will simply be equals to 1 over 2, whereby the opposite is 1 and the hypotenuse is simply 2. What about cos 30? What would that be? We said that would be adjacent over hypotenuse. The adjacent in this case is square root of 3, and the hypotenuse is indeed equals to 2, and that will be square root of 3 over 2. And finally, tan 30 will be indeed equals to opposite over adjacent. The opposite in this case is simply 1, and the adjacent is square root of 3, and that will be 1 over square root of 3. Now you will need to observe the pattern. I give you just a few seconds, pause the video and try to observe the pattern. We can clearly see that cosine of 30 is indeed equals to sine of 60. Similarly, cosine of 60 is indeed equals to sine of 30. And tan 30 is the reciprocal of tan 60. I think that's something that sounds good. So it means you don't need to cram everything or master them. Once you know some, then you just need to know that it is the opposite way or it is the same way as this. That's how it works. Perfect. Now, what about 45? How can we show that? And here it is. So let me get rid of this as we are no more in use of it for now. Good. Now, something just comes to my mind. Some of you might be wondering that why did I use 2 units for my equilateral triangle? It turns out that it's just the best one to use so as to have clearer results. Whichever unit you use, you are still going to have the same answer once you are able to interpret this properly. So that should not be a problem. Now, how can we solve for the corresponding trigonometric functions ratio of 45 degrees as a special angle? In this case, we are going to consider using a square. Let's consider a square of side 1 unit. We know that a square, one of its properties is that all its sides are equal. So if I consider a square of side 1 unit, this will be 1, this will be 1, this will be 1, and this will also be 1. Now at this point, we also know that one of the properties of squared is that all its angles are 90 degrees. They are all at right angle to each other, that is at the vertex. Perfect. Now what I will do next is that I would like to form a diagonal. A diagonal is a straight line from one vertex of its particular shape to the other opposite vertex. So here is a diagonal. A diagonal will split this right angle into 2, which will make this angle to be 45 degrees and this as well to be 45 degrees. Since this is 1 and this is 1, let me bring out the right angle triangle. And this is the part of the right angle triangle. We said this is 1 unit and this is 1 unit. We can clearly solve for this side using Pythagoras theorem. So since this is the longest side, let's assume it is x. We know that according to Pythagoras theorem, the square of x is indeed equals to the sum of the square of the other 2 sides. And therefore, we can clearly have x to be equals to the square root of 2. So right now, I would like to get rid of x and replace that with square root of 2. Okay. Now, don't forget we said this angle is 45 degrees, and this one is also 45 degrees. Perfect. Now, we can now apply the trigonometric functions and see how those functions relate the sides. Now, let's begin with the sine of 45. It turns out that since the both angles in all cases are 45, We don't have to really care about the side or the value of the opposite or the adjacent, because it's going to be referring to the same thing in all cases. So we say sine of angle is indeed equals to opposite over hypotenuse. The opposite in this case is 1, and the hypotenuse is indeed equals to the square root of 2, and that will be 1 over root 2. Now what about cosine of 45? What should that be? It turns out that cosine is indeed equals to adjacent over hypotenuse. The adjacent in this case is simply equals to 1 as well, and the hypotenuse is indeed equals to the square root of 2. And for the last one, which is tan of 45, that one is indeed equals to 1, as the opposite is 1 and the adjacent is 1. And these are the special angle trigonometric ratio that you need to be familiar with. And I hope with this proofs, you should now be able to understand how those values are gotten.